Okay, well, I don't think I have to convince you again of what very interesting systems we have after a common envelope, one or two common envelopes, and this is only for low and intermediate mass stars, so I will just skip to the common envelope phase itself. And we all have been heard a lot about the common envelope efficiency here, this low efficiency that is derived from observations, so I want to review this a bit. So basically, you have the initial configuration, initial orbital energy and binding energy, and you have the final orbital energy, yes, after ejecting the envelope in a much closer binary. And then just relate these two energies, the change in orbital energy with the binding energy of the envelope, with an efficiency. This is the famous common envelope efficiency you have been hearing. That is the fraction of orbital energy that you really use to unbound the envelope, because the common envelope phase is very fast. So you don't expect to use 100% of the orbital energy. So you expect an alpha value below 1. If you get alpha values above 1, this means you are missing some extra energy sources probably that help to unbind the envelope. So it looks really simple, but it's not. We have a lot of questions. Is this lambda a universal constant? And this is what we're trying to constrain here. But also, if you want to constrain alpha, you need to first get an agreement of what you're going to use for lambda. Because if you look at different studies, this lambda, the structural parameter, take into account for the binding energy of the envelope, can be very different from one study to another. Some authors even constrain alpha lambda instead of trying to constrain alpha. So, and the other thing I say, take care, because not always the initial orbital energy is the orbital energy of the core of the primary with the secondary, which is the same final system, basically. Some authors put M1 there, like the whole primary. And the thing that is spiraling in is the core. So in the BSE code, it's this formulation, but not if you look at the Ivanova papers, for example, they put M1. So if you want to constrain alpha and compare with other studies, you need to know what they are doing to be consistent, or if they use something different, to be able to transform. So the lambda parameter, I think, is so unconstrained as alpha, or even more, because in a lot of studies, all studies, they use a fixed value of this lambda parameter, either 0.5 or 1. In other studies, they calculated this parameter, assuming that it only comes from the gravitational energy of the envelope. And in some cases, they also include a fraction of the internal energy of the envelope to help to unbind the envelope. But what is internal energy? And then it goes even more complicated, because you can read in the literature, like especially in the Ivanova et al. 2013 review, a lot of different possibilities, and also very recently convective transport, and a lot of ideas to help to eject the envelope. But if you ask me, I probably think thermal energy is fine. We should include all thermal energy. Recombination energy is the second most attractive one. I don't think it's used, or if it is, it's just a very small fraction. But each one can have its own fraction in this equation. So if you're going to compare, check what they are including. And all of you cited the 2010 paper, alpha 0.25. I have to clarify, this was done for 3 different cases. The first left panel was the reconstruction of white dwarf, not only M dwarfs, the ones above, all the ones that said SDSS are white dwarf, M dwarfs, homogeneous sample. The others are from the literature. So we compared with lambda fixed, 0.5, lambda from the BSE code, which was not published at that time, was finally published in 2014, not explained, just published. And the lambda BSE from the BSE, including internal energy. At that time, I said internal energy, it was really recombination energy, right? And then we derived this range here, 0.2, 0.3, so 0.25, but this is including recombination energy. So, and we did that because there was one system, IKPEC, that could not be reproduced without this extra energy source. So you are citing something that includes recombination energy, you are using 0.25 without recombination energy in your calculations. So be careful, but if you look at the calculations of lambda with and without this recombination energy, the values without recombination energy, but with virial theorem for the thermal energy, which is what BSE includes, looks like lambda more or less 1, but if you include a fraction of recombination energy, then especially in the thermally pulsating AGB phase, so progenitors of massive white dwarfs, lambda goes to very high values, so basically the envelope is really, really not very well bound, so it's much easier to expel it if you include it. So just a tiny fraction of it will be sufficient to explain systems like ICAPEC that indeed needs only 1% of recombination energy, not the 25 in the other calculation. So you're using something that was derived with 25% of recombination energy, which seems today very unlikely. But we don't have to panic because, as I said, for most of the systems, it is not that important, its recombination energy. So if you look at simulations versus observations of the SDSS sample for white dwarf main sequence stars, M stars, also a low value of alpha was derived without recombination. And there is also the paper from Sylvia Tonen and Nellemans in 2013 that they also favored low values of alpha. In this case, it was alpha lambda that they constrained, which I don't like that much, but if you think that in general, lambda without recombination energy is very close to 1, this means that if no recombination is included, this is consistent with a low value of alpha. So that's for the M dwarfs. We are kind of safe. I would prefer to use 0.3 than 0.25, but still it's not such a huge difference. And then I said ICAPEC was a problem, and then in 2014, KOI 3278 also needed more energy, but just 2%, or any other extra source of energy. So we start looking for more systems with massive companions, and we found already, we have characterized 8 or maybe 9, fully characterized, I mean, with short periods, measured periods in the two masses, and all of them are below 3 days in orbital periods, and all of them can be reproduced with a large range of common envelope efficiency, no recombination energy or any extra energy source needed, and low value of efficiency as low as 0.2 for all of them. This doesn't mean it is 0.2 because they all go above 1. I just put 1 there as the maximum because more than 1 it's not physical. But most of the results are in the range where you have still this 0.2, 0.4, so then you get a more likelihood. And finally, very recent, and these two then are outliers. We still don't know. For KOI 3278, I'm not even sure it is a post-common envelope binary. It might even be stable, non-conservative. The ones above are all not PCBs. And ICAPEC, as I said, only needs 1% of recombination energy or anything extra to compute, to get a possible progenitor with common envelope. Finally, very recently, we did the same calculation for white dwarf brown dwarfs, because there were some authors saying that for these ones, you really need an alpha larger than 1, or some extra energy sources. So we did a with Matthias, careful review of the literature of all these systems. There were like 15 systems claimed. Some of them were not even binaries. Some of them, the progenitor was something else, or the period was very, very like 3 points in a sinusoidal that was not fitting everything. So we kept 8 systems where the parameters were believable, and 7 of them had periods below 0.1 day, 1 period of 0.43 day, which is kind of the largest period in this sample. And for one of them, there was only an upper limit for the mass of the brown dwarf. So I calculated with different values for the mass of the brown dwarf. And in all cases, I was able to reproduce with alpha below 1. And also, what's interesting for these systems is that you also have a minimum age for the brown dwarf, because if you can measure the temperature of the brown dwarf, you can use cooling tracks and see the minimum age. Why minimum? Because it can also be heated by the white dwarf. So this temperature is kind of the upper limit for the real temperature, or temperature without this heating. So this gives you a minimum age for the system, and this, in the other systems, you can constrain the lower limit for alpha, but here you can also constrain the upper limit for alpha. And if you want to reproduce all the systems with the same alpha, including the age restriction, then you get a very more narrow parameter that is 0.24 to 0.41, consistent with all the others. So it seems that at least for white dwarfs with non-degenerate companions, or brown dwarfs, I would say non-evolved companions, the common envelope efficiency is in general small, and there is no need for extra energy sources except 2 outliers that we might review. Finally, and this is work in progress, Sarah Caswell was the referee of my brown dwarf paper, so then she sent me this data from one new white dwarf brown dwarf that she's deriving, and she wanted me to reconstruct. And then when I sent the reconstruction, she said, but I need the system to be older. So I was struggling to get an older age because of the minimum age of the brown dwarf. And then I said, okay, what if I try with different grids for possible progenitors, and I use lower metallicity. And then lower metallicity allows for lower mass progenitors, which means you can have less mass in the envelope, so alpha gets smaller, but the time scale for evolution gets larger. So I didn't care much about metallicity before because I just compared these two. I never did the grid with very low metallicity. And then it really matters. And if you go even lower, it matters more, but then it's how likely it is that the system is so old and you can still see it. And then it's because it must be very old to be very low metallicity. But at least for this 0.01, which is not that unrealistic, I reached the age she wanted. So I keep the other one because I wanted to show you how lowering the metallicity will change the results. So as a summary, we need to be consistent when we try to constrain alpha and compare with the results from some others, if they use alpha lambda, if they use same initial configuration, what did they include in this lambda parameter. Also, recombination energy in the vast majority of the cases is not needed, just thermal plus thermal plus gravitational is enough. And in the 2 outliers, it can be even any other source of energy that helps. And if you look at the constraints for the different types of companions to white dwarfs, unevolved companions, it seems more or less similar, although in the first 2 groups it's just lower limits. Only in the brown dwarf companions we can put upper limit. And it seems, this is not unevolved, but white dwarfs, I just read Peter Scherbach is going to talk about, this seems to be also consistent. Of course, this is for the second phase of mass transfer that produced the second white dwarf. I think first mass transfer phase was not a common envelope there. And also, metallicity matters.
Thank you very much. Questions? I was just wondering around metallicity, are there cases where you can actually measure the metallicity of the M dwarf?
No, I don't think so. Yeah, no, I asked, for example, for this one, for Sarah, I asked, do you know more or less, because the system is like between 2 and 3 years old, but they don't know anything about the metallicity.
Right. I mean, 2 or 3 gig years and that low metallicity seems...
Sorry?
That's a pretty low metallicity for 2 or 3 gig years old, right?
The 0.01, yeah, it's still small, yeah. Okay. So it might be that this age is completely wrong.
Thanks.
Because there is another paper published on this system now already, and they say the system is younger and with a lower mass white dwarf. But then it's also tricky, because if I use a lower mass white dwarf, then I get lower mass progenitors, and I get an even older system with normal metallicity. So it fits better with the mass published, but fit worse with the age they published. So I think this system is still, I don't believe these results for these systems. It was just to show you that metallicity causes an effect in the reconstruction.
Thanks for the nice talk. So you say recombination energy is not needed. Maybe that's true, but is it actually used? Do we have data to constrain whether or not recombination energy is actually contributing to the budget?
Well, you have ICAPEC and KOI, but then it can be any other source of energy. As far as I understand, recombination energy, you need to have a very low temperature, so it might be at the very end phases of common envelopes. So if it contributes, it should be so short, the moment when it can contribute, that I don't know if this will make more efficient the process or not. It might help in some extreme cases, like ICAPEC with a very massive white dwarf or so, but I think it's not the general, in general, people is neglecting this effect, and I think that's fine for most of the systems, but the contribution might be small.
Sure, but are there any clear empirical constraints?
No, I don't think.
Yeah, okay.
Empirical, I think no.
Okay.
From the models, they said, yeah, well, less than 10% should be. That's hydrodynamic models.
So I think that's very interesting. Do you have any idea why the metallicity makes a difference? Do you more think about do you think that in the common envelope itself it makes a difference, or that it somehow changes the stars that go into common envelope, and that's why it's different?
It's the core mass, because the core mass of the star and the evolutionary timescale for the progenitor is affected by the metallicity. So if you have a lower metallicity, your grid of possible progenitors is different. They go towards lower masses, and they can still evolve, and so it's not related to the common envelope itself.
Okay, I have one last question. So you reconstructed all the systems, and for the M dwarfs, you also compare. Well, you cited papers that compare the distributions of periods. So for the other samples, wouldn't it be also good to run a population synthesis with the correct?
But the thing is that, for example, the Camacho et al. Paper compared with simulations with the observations, because you had an homogeneous sample of like 50 white dwarf M dwarfs. If you have white dwarf AFGK stars from the same survey, but you only have 8, I don't think simulations are still good enough. We are starting, but it's still too few observed systems to really do statistics.
Okay. Yeah, more questions? Doesn't look like, so we have a coffee break. Thanks, Monica. Thanks all the speakers.